Energy storage in carbon-based supercapacitors depends on charge uptake in the carbon electrolyte interfacial region, which relate to the surface of chemical and electronic structure of porous carbons. Porous carbon materials with a well-defined oriented pore structure are of great importance for energy storage because of facilitate ion transport. Besides, porous carbon materials, in particular boron-containing, are of show great importance from the point of view of gas storage, for example, hydrogen. That's why the aim of the work is determination of conditions and peculiarities of the obtaining of boron-containing nanoporous carbon materials by bulk and matrix carbonization of sucrose in the presence of boric acid, the study of the structure, sorption properties by nitrogen and hydrogen, and the electrochemical properties of the obtained materials. For obtaining of boron-containing carbon materials, we use matrix carbonization and bulk carbonization. Matrix carbonization was carried out in mesoporous molecular sieves, silica mesoporous molecular sieves, SBA 15 type. For this purpose, this porous silica was impregnated with solution containing containing a certain amount of sucrose, boric acid, and concentrated sulfuric acid at the rate of 1.25 gram of sucrose, 0.14 gram of concentrated sulfuric acid, at 1 gram of porous silica. The weight ratio of boric acid to sucrose was following. The temperature of carbonization was 900 degrees. Silica matrix after reaction was removed via dissolving the obtained composite in hydrofluoric acid. For obtaining of microporous boron-containing carbons, we used bulk carbonization of sucrose. In the presence of boric acid, the weight ratio of boric acid to sucrose was the same. The temperature of carbonization was 900 degrees too, and the time of carbonization was 2.5 hours. The content of boron in the synthesized carbon materials is 1.5 weight percent. For this purpose was used acid-based titration by using of mannitol, was used for determination of boron content. According to X-ray diffraction for the obtained mesoporous molecular sieves, CMK3 type, boron-containing, these materials have a high degree of spatial ordering because position, intensity, and dividing of low-angle reflexes are close to those of CMK3, which have no boron. With the increasing of the content of boron acid in the mixture for impregnation of silica matrix, and during obtaining of boron-containing mesoporous materials leads to decreasing of the position, decreasing of the intensity, and dividing of low-angle reflexes. The maximal used ratio boric acid to sucrose 0.2 leads to a significant decrease in the position of in the intensity of these reflexes, which is evidenced by the preservation of a single low-angle reflex of low intensity. At the same time, the broad low-intensity peaks at 20-26 degrees and 44 degrees testify about predominantly amorphous nature of the framework of obtained carbons, probably with minor fraction of graphite-like fragments. Electron microscopy shows monolithic structure of the obtained carbon materials. At the same time, the obtained microporous boron-containing carbons are more compact than the samples without boron. Mesoporous boron-containing carbon materials have hexagonal mesostructure, such as which is typical for CMK3 type carbon. In the result of matrix carbonization of sucrose in mesoporous molecule CIFS SDA15 type, in the presence of sulfuric catalyst and boric modifier acids with follow dissolution of silica matrix, mild activation of carbonization of sucrose is observed, which leads to formation of mesoporous carbon materials and compaction of the carbon phase in mesopores, and thus a significant increase in mesopore diameter, volume, and specific surface area compared with traditional process. In similar condition, the temperature 900 degrees bulk carbonization of sucrose in the presence of boric acid leads to the formation of microporous boron-containing carbon materials. Micropore volume is up to 0.3 cubic centimeter per gram. At the same time, with increasing of boron content, decreasing of micropore uniformity with increasing of their size is observed, and the potential of nitrogen adsorption decreases from about 4 to 3.2 kilojoule per mole. According to measurement of hydrogen adsorption for synthesized mesoporous carbon material CMK3 type, without boron and boron-containing such materials obtained by matrix carbonization, adsorption capacity for hydrogen is close and is about 1.2 weight%, and it was observed that specific hydrogen adsorption on the pore surface has very high values, and the potential of hydrogen adsorption remains practically unchanged, is about 4.7 kilojoule per mole. Hydrogen adsorption for obtained microporous carbon materials obtained by bulk carbonization of sucrose in the presence of boric acid is significantly higher than for mesoporous ones, and is about 1.55 weight%. A comparison of adsorption parameters of hydrogen and nitrogen adsorption testifies that for initial and boron-containing carbons, there is a decline of specific adsorption in micropore volume from 53 to 37 milligram per cubic centimeter, and significant increase of hydrogen adsorption potential is observed from 5 to about 5.3 kilojoule per mole. The effect of increasing of the adsorption energy for hydrogen on the surface of boron-containing carbon is probably due to the incorporation of boron on the surface of a carbon framework and inside, and the adsorption of hydrogen on boron-containing adsorption centers. Modification of porous structure in the presence of boric acid, probably due to changes in proportion, micropore and supermicropore size, uniformity, and formation of narrowing in micropores with increasing of boron content in boron-containing carbon materials, and corresponding increasing in the adsorption potential of hydrogen molecules. The obtaining boron-containing materials were tested as supercapacitors. Measurements were performed in 3 electrode cells. The working electrodes were prepared by mixing of carbon powder with a solution of polyvinylidene fluoride, further drying and pressing into thin tablets. For the prepared electrodes, capacitance was measured and stability during cycling was tested. It was shown that the capacitance of the obtained carbon materials, special microporous carbon materials, is up to about 300 farad per gram. The capacity of such materials is due not only to the capacity of electric double layer, but also to the presence of reactive surface group, which can enter into redox reaction. The obtained materials are stable during charge-discharge, during repeated charge-discharge cycles. The conduction of 25 cycles does not change the capacity and the form of cyclic volt-ampere gram. The obtained boron-containing materials show large gravimetric and interfacial capacitance. In contrary to carbon without boron, which are not electrochemically active. This is stipulated by incorporation of boron into carbon framework and formation of surface chemical structures. Boron-containing carbon materials, carbon samples, exhibit superior interfacial capacity 0.18 or 0.36 farad per square meter for meso and microporous carbon respectively. So, meso and microporous boron-containing carbon materials were obtained by methods of bulk and matrix carbonization of screws in the presence of boric acid. The obtained materials show large pore volume, uniform pore structure, large specific surface area, and they are characterized by high adsorption of hydrogen and interfacial capacity that is 1.52 times higher than those in literature. Thank you for attention.
Some comments or questions for Dr. Shcherban? Please, Professor, question.
Can you show slide 7? Okay, can you explain what is on horizontal axis here and some explanation about this box?
This is a term of nitrogen absorption-desorption. This is relative pressure. And this is pore diameter.
What is this?
This is pore size distribution. Pore size distribution and other terms. This is a distribution for micropore.
Okay.
This is nitrogen absorption-desorption and the data from it.
How to explain this dots? How to explain such results?
Bulk in the result of bulk carbonization of hydrocarbons such as sucrose, we obtained typical microporous materials. Typical microporous carbon, it has only micropore. Its volume is 0.3 cubic centimeter per gram, and not other type of pore, not mesopores, not micropores. It's typical microporous materials, and that's why we have such form of. It is the plot of the first type. It is other term of first type and correspond pore size distribution. Only micropores.
And this maximum at this size? And
this maximum is maximum from this picture. And from this picture we have micropore volume, and from this picture we have micropore diameter.
Other questions, please? Yes, please.
It is well known that boron atoms as well as nitrogen atoms are very popular impurity atoms for substitution of two-dimensional carbon. In your boron-containing nanoporous material, what concentration of these atoms and what their configuration? Do they substitute atoms? And are they random or maybe correlated?
The concentration of boron atoms is from 1 to 1.5 weight percent. From the literature, it is known that boron there are incorporated boron and boron on the surface. So there is the bond boron-carbon and bond boron-oxygen on surface. And now we wait for results of X-ray electron spectroscopy to know exactly the fraction of those boron.
Once again, I don't understand this unit. This is nanometer?
Yes, nanometer.
So 0.4, it is the size of single atom.
Maybe.
So the pore is 1 atom?
The pore is 5-6 angstrom.
This is the diameter of single atom, 0.4 nanometer.
It's more than...
Fluoride, for example. Starting from 0.2 to 0.4.
About
But
maybe.
you are saying that it is the size
It is more
of pore.
About something new.
So is atom defect?
It is
Yeah.
no, it is molecular sieve, typical microporous molecular sieves with very small pores. Pores of
But it is
0.5.
diameter of single atom.
It's more than the diameter of single
Some
atom.
unit is not right here.
It's more than diameter of molecules. For example, hydrogen, there is some layer of hydrogen molecules, for example, and for nitrogen molecules. They are adsorbed gases, hydrogen, nitrogen. So we have other terms of adsorption, desorption. This is molecular sieves.
I am student. I am thinking like student, asking you to explain me. Surprised that you are using the size of pores, like the size of single atoms. Why?
Several times more than atom.
Several times more. It's more than one molecule.
Ah,
It's more than molecule. Molecule can enter there. Molecule of nitrogen, molecule of hydrogen.
is higher than single atom.
Yes,
but
yes,
it has
yes,
some
of course. It's higher.
It is fluoride.
Fluoride is larger.
We thank you
Okay.
again. For the poster session.